So students, today we are going to learn about a very important property which is called the Lanthanoid contraction, and this is seen among the Lanthanoid elements of the periodic table. So before going in detail, I would like to tell you about what are the topics I am going to tell you here. So first I am going to tell you what is Lanthanoid contraction and its definition. Then I will tell you about the reasons behind the Lanthanoid contraction, that means why this Lanthanoid contraction is happening. Then I will tell you about some important consequences of this Lanthanoid contraction, and at the end of this lecture I am going to tell you some of the problems which generally comes in the examination related to this Lanthanoid contraction. So what is Lanthanoid contraction? Lanthanoid contraction is basically the contraction of the atomic radii or the ionic radii in lanthanoid elements. Ionic radii means the radii for the tripositive ions of lanthanides. You see here is a graphical representation where in the x-axis we have the atomic number for lanthanum to lutetium, and in the y-axis we have the ionic radius for Ln3+ ions, and here you see the value, it has decreased from a value of 105 picometer to a value of 85 picometer, and this 105 is for La3+ ion and this 85 is for lutetium Lu3+ ion. This decrease is not very regular in case of atomic radii, but for ionic radii this is a very steady decrease, and this all is happening because of the filling up of the F electrons in the lanthanoid series. Here is the periodic table, and you know very well the position of the lanthanides in the periodic table. Actually they are called the inner transition elements as they are present inside the transition elements. So this is the 6th period, and here the lanthanoid elements are present, and they have the atomic number starting from 57 to 71, and they are actually A block elements. So now we will learn about the general electronic configuration of these elements. General electronic configuration of lanthanides are as n-2 F1 to 14, then n-1 D 0 to 1, and ns 0 to 2, where n is equal to 6. That means it will be 4f1 to 14, then 5d 0 to 1, and then 6s 0 to 2. Here is a table which gives us the atomic number for the lanthanides and their name, their symbol, then their electronic configuration in the atomic state and also in the ionic state, and their metallic radii and ionic radii. So if we look at their electronic configuration, you can see gradually the F orbital is being populated, and here you see the ionic radii of La3+ is 106 and Lu3+, that is lutetium 3+, is only 85. So it is very prominent that there is a gradual decrease in the ionic size. In our previous slides, you have seen the general electronic configuration for the lanthanoid series, and it is 4f1 to 14, 5d0 to 1, and 6s2. Here I have shown you pictorially that you see this is the 6s orbital, that is the valence shell, and then comes the 5d orbital which is called the penultimate shell, and inside that there is the antipenultimate 4f shell. So what is happening basically, as we are moving from left to right in the lanthanoid series, this 4f orbital, that is the inner shell, that is the antipenultimate shell, is getting filled up gradually. So what will be the effect of that? You know that the 4f orbital is very much diffused in shape, and other than that these electrons are very poor shielder of nuclear charge. And what will be the effect? If the nuclear charge is not shielded up properly, what will happen? It will drag the outer electrons and outer shells towards it, and the result will be the shrinkage of size, and that is happening here, and that is the main cause of lanthanoid contraction. So whatever I have told you in the last slide, I have written here clearly, so you can read it again, that as the atomic number increases in Lanthanoid series, for every proton added, that is as the atomic number is increasing to the nucleus, the extra electron goes to fill up the 4f orbitals that you know now. Now these 4f electrons constitute inner shells and are not so effective in shielding the nuclear charge as the shielding effect of S greater than P greater than D greater than F. And these electrons actually cannot shield the nuclear charge, and what happens? The shrinkage of the electronic cloud takes place, and that's why there is a gradual decrease in the size of the lanthanoid ions with increase in atomic number. So now comes the definition of lanthanoid contraction. So we can say that the overall decrease in atomic and ionic radii from lanthanum to lutetium due to imperfect shielding of 4f electron from nuclear charge is called lanthanoid contraction. So decrease in atomic radii for lanthanides are not as smooth as in M3+, that is Ln3+ ions. And you should always write that because of this, the ionic radii of cerium 3+ is 103 picometer and ionic radii of lutetium 3+ is 85 picometer, which is shown in this graph as well. Now, some very important things. So these are the consequences of lanthanoid contraction. So I am going to discuss here about 3 consequences of lanthanoid contraction. So they are like we can explain the similarity in properties of 4D and 5D series of transition elements, and we can also explain why the separation of 4D and 5D series of transition elements become difficult. These 2 topics are interrelated. Then we will be also able to tell about the basic strength of hydroxides of lanthanides. So here I'll discuss these 2 topics together, as I have already told you that they are interrelated. Actually, from 4D to 5D series means we are going down group wise, and you know very well when we go down group wise in the periodic table, the atomic or ionic radii value should increase because of the incorporation of new cells in the configuration. But in case of 4D and 5D series, it is very surprising to note that the sizes of the elements remain almost same. So these are the 4D and 5D series of elements present in the periodic table. So these 2 series are transition elements, and you see here this zirconium, hafnium, niobium, tantalum, molybdenum, tungsten and so on, they are actually present in the 4D and 5D series. And you will be surprised to note that the atomic and ionic size for all these pair of elements are nearly same, and they are actually called, this 5D series is called the post-lanthanoid elements because they are present after the lanthanides elements had intervened in the periodic table. And for understanding that, you have to know about the electronic configuration of these elements. You see here I have taken one example, like for zirconium it is a krypton, then electronic configuration will be 4D to 5s2, and for hafnium it will be xenon and then 4f14, 5d2 and 6s2. So what is the difference between these 2 elements electronic configuration? The main difference is that there is an incorporation of these 4f14 electrons, and these are very poor shielder of nuclear charge. So this makes all the difference. We are going down, number of cells are increasing, but still the ionic or atomic radii is not changing. So the reason is that because of the lanthanoid contraction, that is decrease in the atomic or ionic size, these 2 elements will have nearly same atomic or ionic size. And you see In case of zirconium, the atomic size is 159 picometer, and in case of hafnium it is 156 picometer. So comparable sizes. And then in case of zirconium 4 plus ion, the radius is 80 picometer, and in case of hafnium 4 plus ion, the radius is 81 picometer. So they are also nearly having the same values. So effect of lanthanide contraction is very much prominent in this 4D and 5D series. You see here, these are the three transition series. This is 3D, this is 4D, and this is 5D. And if we go from 3D to 4D, this is in the y-axis, the radius is there. If we go from 3D to 4D, there is quite a bit of increase in the atomic radii. But if we go from 4D to 5D, they remain almost same. So this graph tells you that the atomic radii of 4D and 5D series are nearly same. And this I have already explained you. This is only because of this lanthanide contraction. And what happens for that? As the atomic or the ionic radii is same, the physical and chemical properties for these 4D and 5D series elements will be same. And the physical properties like melting point, boiling point, ionization energy, electron affinity, electron negativity, they also control the chemical properties. And the result will be that it will be very difficult in separating these elements from each other when we try to get a pure compound from the ore of these compounds. A very important consequence of lanthanide contraction is the basicity of lanthanide hydroxide. Basically, you know how we are going to tell about the basicity of any hydroxide compound. It will depend on the number of hydroxide ions it gives upon dissociation. So, for lanthanide hydroxides, if we break this bond, it will give rise to Ln3 plus and OH minus. And this OH minus is responsible for the basicity of the compound. Now, how this will be dictated by the ionic radii of the compound, that we will learn. So, remember Fuzan's rule. Fuzan's rule tells us that as the size of the cation decreases, it will pull up the electron density of the anion more towards it, and it will give rise to a covalent bond. So, as the size of the cation is more, it will give rise to a ionic compound, and if the size of the cation is less, that is small, then it will give rise to a covalent compound. So, what do you think? This bond to be dissociated, the compound should be ionic in nature. But you know, when because of this lanthanide contraction, when we move from left to right in the lanthanide series, that is from La3 plus to Lu3 plus, the compounds, actually the ionic size of the Ln3 plus becomes less. It decreases. So what will be the effect? Actually, the compounds will be more covalent in nature. They will be less ionic in character. So what will happen? Actually, the dissociation of this bond will be difficult, and the result will be that the basicity of the lanthanide hydroxide will decrease as we go from left to right. So now you will be able to tell why the basicity of the lanthanide hydroxide decreases as we go from lanthanum 3 plus to lutetium 3 plus. And now there are some questions related to this lanthanide contraction, which I am going to tell you, and I think you will be able to answer all of them. Like, what is lanthanide contraction? Discuss its causes and consequence, that you have learnt already. Now, why does the ionic radii decreases steadily from Ce3 plus, that is cerium 3 plus, to lutetium 3 plus? This is also, I am sure that you will be able to answer, because if you see this, you will understand that they are basically they belong to the lanthanide series, and this question will be answered using the lanthanide contraction. And then again comes explain why zirconium and hafnium show similar chemical and physical properties. This also I have explained you earlier. And now, why is it very difficult to separate niobium and tantalum from their ore? This is also a 4D and 5D series elements they are. So they will be having the similar physical and chemical properties because of lanthanide contraction, because their ionic size and atomic size will be nearly same, and so it will be difficult to separate them from their ore. And now the last question is that comment on the basicity of the hydroxide of lanthanides. That also I have told you just now. So you will be able to answer all the questions. So I think today I am going to finish it here, and I will be very happy if you can answer the questions in your examination related to this lanthanide contraction. And thank you, and I will see you in my next class.